everyone, my name is Suborno Isaac Berry from Berry Science Lab. You guys all requested a linear algebra series, so welcome to, let me see, does this work? Yup, lecture 1 of linear algebra. I'm doing this on the go, so I apologize if there were any difficulties. But today we're going to learn about the most basic concept of linear algebra, vectors, and maybe a little bit of matrices. So if you've taken pre-calculus before, you've probably already heard of what vectors are. But to review, in two-dimensional space, which is what most of you will have worked with before this course, so that's represented by this symbol, R2. So in two-dimensional space, you can pick some point in the plane. Let's say this one. Hopefully you all understand what a point is from geometry class. So then, let's say we draw a little arrow to this point. So, now let's call this arrow U. Whenever we have a vector, we put this little arrow on top of it so as to not confuse it with a scalar. What is the difference between a scalar and a vector? Well, a scalar is a regular number. So, for example, 17, 71, pi, e, all of these are just scalars. And even most of the variables you've worked with, probably all of them are scalars too, because of the unique defining feature that vectors have.
Can we say scalar 2 plus 2 is always 4? Vector 2 plus 2 can be 4, can be 0?
Well, we'll explore that later on, when we come to vector arithmetic. Ouch, I got a cut here, didn't I? So, a vector could be something like a displacement vector. We'll show you what that means later on. It could look something like this, like a set of numbers. Or it could be denoted by a symbol, just like that. So all of these are ways to show what a vector is. So, why is it different from a scalar? This looks kind of like a list or a set, right? Well, that's exactly what it is. So, when it comes to scalars, if we have 17, which is one scalar, and then we have another scalar of the same magnitude, which would also be 17, these two are the same thing. But if we have a vector, and then we have another vector of the same magnitude, then they are not the same because clearly they are still pointing in different directions. So, how can we quantify the magnitude of a vector? Well, given any vector, what we can do is we can translate the tail of the vector all the way to the origin, and then we can calculate the distance between the origin and the head of the vector. So that's how we quantify magnitude. It's basically the distance between the tail and the head. And I mean, direction is of course direction, but how we quantify it is pretty unique. We measure the angle, and hopefully you know what angle is, starting from the x-axis right here. So this angle would be theta, for example. So that's what a vector basically is. Let's do a short example. So, using what I just told you, let's say we have A is equal to 3 and B is equal to 3. Is A equal to B? Then let's say we have a vector C is equal to 6, 8, while D is equal to minus 8, 6. Is C equal to D, given that they both have magnitude 10? And then, finally, E is equal to 7, 5, and F is equal to 7, 5. Is E equal to F? So, take a second to think about these examples, maybe post them in the comments, and I'll tell you the solution next time. So, these are the core concepts that I want you to get. Now let's take the eraser and cover what we call vector arithmetic. Now the thing is, we're mostly going to be working with R3 in this course. What is that? Well, it's shorthand for the three-dimensional space that we live in. But for now, to gain some familiarity, we're going to still work in R2. So, now we're going to cover vector arithmetic. So, when normal arithmetic comes to your mind, you think of addition, scalar addition, scalar subtraction, scalar multiplication, and scalar division. And vectors actually have 3 of those 4 operators. Multiplication is a little bit different. We'll get to those later. But unfortunately, division has no direct parallel with vectors. So, first of all, let's go over vector addition. Now, notice when I said vectors can be denoted as lists of numbers. What does that really mean? Well, let's think of these with parentheses instead. This is just a point in the coordinate plane, right? So it's the point at x equals 3 and y comma 4 right over here. So then the arrow from the origin to that point can be represented as that vector. As long as you conserve its length and direction, you can move it anywhere around the board. So kind of like if I take this pencil from my desk, if I give it a certain direction and it has a constant magnitude, as long as I keep those two things the same, I can move it anywhere in the coordinate plane I want. The only two things quantifying it are its length and its direction. So talking about length, you can find the length of a vector, also known as its magnitude, usually denoted by taking the absolute value of it, or putting 2 bars around it so you don't confuse it with the absolute value. So this is how you're mostly going to denote the magnitude of a vector. So let's say u is 3, 4. Then the magnitude is just, by the distance formula, the square root of 3 squared plus 4 squared, which is equal to the square root of 9 plus 16, or the square root of 25, which is 5. So the magnitude would be 5. So that's an operation you can do on a single vector. So now let's cover addition. So we can really treat them like lists of numbers in a lot of ways. So if we wanted to add together the vectors 3, 4 and 8, 15, then what do? Well, we can just add the separate components together. 3 plus 8, 4 plus 15, which becomes 11, 19. But what is the geometric intuition of this? How can this be represented graphically? Well, let's look at that. So we have x and we have y. We have this vector 3, 4, and then we have the vector 8, 15. I'm not sure if I have enough space to accommodate it, so I'm going to actually shrink my coordinate axes. So this is 3, this is 4, zoom out a little bit. This would be 15, I think, and this would be 8. So then, the thing is, one of our vectors looks like this, and let's do a more down-to-earth example. I'm sorry. Let's do a more down-to-earth example. If we have 6 and 8, no, that's parallel. Let's do 8 and 6. Sorry. So we have 3 plus 8, 4 plus 6, which is 11, 10. So then, let's draw that. This is 3, 4, and this is 8, 6. Alright, so then we have this vector right here, and we have this vector right here. So now what we're going to do is, remember when earlier we said we could find the magnitude of a vector by basically just putting the tail right on the origin? Well, now we're going to act like the head of this vector is our origin. So we're going to carefully place the tail right onto the head. And this is called the head to tail method. This is another way to add vectors. So then you can draw it sort of like this. And now, what does that really mean? Well, if we erase this, then this diagonal right over here is going to be the new vector, what we call the resultant vector. Why is that? Well, let's say this is u and this is v. Let's draw a detailed diagram. So we have u, v, and the resultant, which I'm going to call r. So then, this is the x-axis and this is the y-axis. And you can see this is uy, this is ux, this is a vy, and this is vx. So as you can see, the resultant vector has component ux plus vx and uy plus vy, just like we said right over there. Cool, right? So that's how we can represent addition. So then subtraction is basically the same stick. All you do is just subtract numbers. But there's an interesting relation between addition and subtraction. If you have u and v over here, you can already notice the same thing that I said to you, that this is u plus v. But the cool thing about it is that if we make a full parallelogram with these, then the shorter diagonal in this direction is going to be u minus v. So this is pretty important. Wait a second. Yeah, I'm pretty sure it's actually v minus u in this case. Sorry. So that's pretty cool. Now, why is that intuitively possible as well? Why can, when we have u and we have v originating from the origin, the connecting line between their two heads is going to be v minus u? Well, let's imagine that. So v minus u, the components, as we said before, are going to be vx minus ux, comma, vy minus uy. So then we have, we have uy right over here, and we have vy right over here. And you will notice that since vy is less than uy and we're subtracting, the resultant vector actually has a negative y component, which is why it's pointing slightly to the south. So then we have ux and we have vx. And this is why the resultant has a component of vx minus ux. So that's the rationale behind the two diagonals of the parallelogram. Now, no, we're not done yet. We're not even close to done. So we've got addition and subtraction down. By the way, I'm going to give you, let's erase this because it's really cluttering up our board. I'm going to give you a quick tip because so far I've been giving you the x-coordinates and the y-coordinates of a vector and telling you to make do with that. Now that's easy, but sometimes problems will give you the magnitude of a vector and its direction, and you have to find ux and uy. Now, how would we do that? Any ideas? Well, that's exactly what trigonometric functions are for. Now, if you remember, there are several functions defined on a circle and a hyperbola too, but hyperbolic geometry is not something we're going to talk about in this course. So we have the x-axis right here, and then we can draw some line right through the center, and we're going to pretend this is the origin, and then we have some angle theta here. Now, usually, when we define sine and cosine, we make this 1. But that just means that if it's actually length r, then we just multiply sine and cosine by r because of the principle of similar triangles. So then, this altitude all the way down here is equal. So if this is r, then this is going to be equal to r sine theta by definition, and this is going to be r cosine theta by definition. Now, let's erase the circle around it. Note that this altitude makes a right angle with the base. Now, does this in any way look similar to this? So this is going to be ui, and this is ux. I think the point should really come across here that ux is just going to be equal to the magnitude of u cosine theta. Theta is this angle, and uy is equal to the magnitude of u sine theta. So that's just another thing. So now we've completed vector addition and subtraction. Now I'm going to talk about something actually unique to vectors, and this is what is known as the dot product.
Is that vector multiplication?
It's an analog to vector multiplication, you can say, but it has some very useful properties that we're going to talk about in a bit. So, if we have two vectors, let's say we have 2, 5, and 7, 9, then the dot product between them is going to equal to 2 times 7 plus 5 times 9, which in this case is equal to 59. So, why is this dot product important? Well, I'm not going to show you the proof today. I'll probably show it to you tomorrow. Well, not tomorrow actually, but next time we're on the series. That the dot product can be formulated just like so, where theta is the angle between the two vectors. Now, you may have been expecting a vector times a vector to be equal to a vector, just like a scalar times a scalar is equal to a scalar. Now, there is another vector product that we will talk about shortly that satisfies that rule, but it's in 3 dimensions only, so it's less general. But it's still very useful. So we have u dot v is equal to the magnitude of u times the magnitude of v cosine the angle between them. Now, what does that mean in specific? Now, that means that if the two vectors are perpendicular, as in 90 degrees apart, or pi over 2 if you're the little rapscallion that uses radians in my audience, cosine of 90 degrees is 0. So then, u dot v equals 0. When two vectors have this property, we call them orthogonal, which is just a different way to say perpendicular. So that is the main reason why dot products are useful. If we take the dot product of two vectors and see it's 0, well, either the magnitude of one of them is 0, which would make them not a vector, so that doesn't count, or cosine theta is 0, meaning they're perpendicular. So that's the rationale behind the dot product. Great. So now let's cover the vector product that actually gives you another vector, known as the cross product. Now we can't actually define them well because I haven't given you the introduction to matrices yet, but I assure you matrices are nothing hard. You'll learn them pretty easily. But still, I'll just throw out the definition. So, why is this useful? Well, in R3, so let's draw a quick diagram of R3. If we have two vectors in space, perpendicular or not, there is exactly one vector. Well, actually, there's exactly one direction. There are infinitely many vectors, but they only vary in magnitude and not direction. There is only one direction that is perpendicular to both. So any vector in this direction will be perpendicular to both vectors already existing. Now, why is this only defined in R3? Well, because in R2, if you have two vectors, there's only a chance for a new vector to be perpendicular to one or the other. No way to be perpendicular to both, because we don't have that added dimension. And in 4 dimensions, which I can't generally depict, but I hope you get why it's there, if we have two vectors, maybe if we have 3 vectors, we could find something perpendicular to all of them. But if we only have 2 vectors, you can't find a third perpendicular one. Now, what's the formula for this? Well, in 3D space, it should be expected that you have 3 coordinates for each vector, x1, y1, z1, x2, y2, z2, and it's going to give you a third one back out. So you have to use matrices for this. So I'm just going to do the math in the corner because I forgot how to do it in my head. So the answer is going to be x3, y3, z3, where x3, in terms of x1 and x2, is going to be y1, z2 minus z1, y2. Y3 is going to be z1, x2 minus x1, z2, and z3 is going to be x1, y2 minus y1, x2. So, I don't know why this says 0. So, this is the definition of the cross product. And I'll show you a proof of it later. Oh, speaking of, you might be wondering what these are actually. These, I can cover it today, are the unit vectors in 3 dimensions. So in 2 dimensions, the unit vectors, also known as the basis vectors, we'll get to basis very late in this course. The basis vectors are I and j. They are vectors of length 1 pointing in the positive x and y direction respectively. And nothing really changes when we add k. It's just a vector of magnitude 1 pointing in the z direction. Oh yeah, and usually it's not oriented like this. Usually the plane is oriented this way for some reason. Not the plane, the 3-dimensional Euclidean space. So, there we go. No, we are not done. Alright, I'm so sorry, Dad.
How long?
A little bit more. A lot more. Yeah.
Yeah.
So why is this useful? Well, basically, have you ever heard of a plane? If not, that's okay. Well, you've probably been talking about the plane in geometry throughout the entire class. But a plane is basically a 2D surface in 3D space. So you can rotate it one way, you can rotate it the other way, and you can translate it throughout space. It's pretty cool, right? But it's not like this paper, it's infinite. just like the Euclidean 2D space. So, the thing is, if I have any two vectors in random directions, chances are there is only one plane that contains them both. So if I rotate it around one of the vectors to keep it inside, the other vector will be left out. And if I translate it to keep the other vector in, suddenly the first vector is out. Now, there are special, very special cases where three vectors can be coplanar, just like 3 points in your geometry class can be collinear, i.e. lie on one line. But those are very rare. So in general, given two vectors u and v, there is exactly one plane that contains them both, unless u is a scalar multiple of v. So then we can use the plane equation to calculate the actual equation of the plane, the actual form of the plane. Now we're going to get to 3D geometry and coordinate equations later, probably the third lecture. So this is how vectors work, and they're a very useful object in all of the linear algebra, so expect to see tidbits of them later on. So that's it for the first linear algebra lecture. I hope it satisfied all your linear algebra needs, and see you next time.